Yes,
Would
I
it
would
be
love to. Oh,
possible really quickly,
Totally.
Joseph? Yeah, stop screen sharing. There you go. Got it.
Thank you. Yeah, I was just going to say, oh my goodness, what fascinating talks. And I'm so excited about all the capabilities and potential. And I'm sure all of you are thinking, hopefully, at great pace as to what could be possible with this new program. I think I'm going to kick it off actually first to a question for both Peter and for Joe. It seems like we have potentially quite a lot missing in terms of infrastructure. So sort of what is needed on the ground in terms of data collection and then data communication to actually get us somewhere where we're doing predicting and monitoring of pandemics. If you could each from your own perspectives sort of give us your over to you, Peter, first, and then over to Joe, your perspective on what is really missing in terms of the infrastructure that's needed, where this needs to happen on the ground.
Yeah, I think it's a really good point. The problem I see is that diseases tend to begin in rural areas, remote areas, because it's where human populations are making contact with wildlife species for the first time. So, you know, it tends to be very remote areas or rural populations that are often poor. These are in tropical, subtropical countries. So there's a predominance of developing countries with less capacity funding to do the work. So the gap I see is connecting those rural populations and what's going on there with some of the really detailed, big scale surveillance programs that are being done in cities around the world. I mean, so, you know, I was just in China with the WHO mission looking at the origin of COVID. China has an incredible infrastructure in the cities of pneumonia surveillance and blood donation. But of course, in rural Yunnan, where maybe this virus first got into people, or perhaps in countries like Myanmar, it's just not there. So what I do see as a way out of this is research programs and projects that work in those rural areas and sort of mirror the data that's then collected in the cities and try and link the two and scale them across. And understanding the scales will be critical to understanding risk. Over.
That's just right. Thank you, Peter. Joe, do you have thoughts on that?
Yeah. As Peter mentioned, we are developing the tool that can facilitate this type of glucose meter-like device. If you can do, we are doing a TB, tuberculosis, for low resource setting in India, for example. So why not to use similar technology for widespread? This meter costs $10. The strip costs $1. So this really can be scalable at a low cost. I agree with Peter. Yeah.
I guess, Joe, just to follow up then, I think we're super curious as to how those sensors that you were showing across different biomarkers could potentially be adapted for animals, even wildlife, where we just have, you know, hands-on access over maybe a few minutes or hours. Of course, there's the issue of fur, and that fur will grow back. What do you think are the possibilities there?
No, we got interest from the pet business community for over a decade to monitor pets, dogs, and cats in general for diabetic, for example. This is so it's really adaptable not only for blood, even sweat of horses. We do lactate in horses for sport applications. So it's all can be adapted with proper investment for sure. Yeah.
That's great to hear. Over to you, Neon.
Yeah, I very much enjoyed the presentations, both great talk and great work. So I have a question for Joe and for Peter. So the question for Joe was, you have been working on different kind of sensors, and sensitivity and specificity are the two key parameters as a sensor design engineer. We always work on that on a daily basis. So what's your experience for your own sensors, Joe, when you design your own sensors for glucose, for different biomarkers, for disease diagnosis? So this is a question for Joe. And the question for Peter is that if we have a sensor that can detect pathogens from the air directly, now the question is, can we station those sensors in like wild animal habitats, like the bat caves, for collecting data from like their droppings, the urines, etc. There will be a lot of pathogens in the air that are out there in the habitats. So can we do that? For example, for identifying the animal hosts? Thank you both.
Maybe I'll start. So again, sensitivity is always the limit, but that's why we're extending the assay time. Instead of 10 seconds for glucose. Glucose is the millimolar concentration in blood. We can do it in 5-10 seconds. For the antibody antigen assay, even going, we have project on diabetic like insulin, which is picomolar or femtomolar. We can do it in 20 minutes in decentralized setting. So the only thing we need more time for the incubation, for the binding event, and then we use a lot of amplification scheme to push the detection limit to the low picomolar concentration in a matter of 20-25 minutes. It's still in a low-cost, decentralized, disposable device. Peter, please.
Sorry, I'll pick up on the sensor question. Really good. I mean, absolutely, that could be done and would provide really interesting data. And, you know, there's been work in the past, going back a few decades, on trying to do remote sampling of mosquitoes. And I know in northern parts of Australia and over into the Torres Island Straits, people were trying to set up sensors so that mosquitoes would be attracted to baits over a period of 6 months and then get killed and preserved. So you could get the blood meal and do DNA sequencing, you can get the viral load, etc. when you go and pick it up. So it's all about scales and cost. The very best work will be done by people going into bat caves, catching bats and sampling them, looking at how does the virus prevalence change from sex, age, species, all the rest of it. But there's a lot that could be done with sensors to fill in the gaps and to expand the scale of the surveys. And as long as that's then tied back to the real data on contact, it matters. I think it's going to be really useful. The big question on contact is aerosol how it's spread to other bats, or is it how it's spread to people or livestock? And there has to be some experiments around that to find out what the answer is. And then that makes more sense of what you get from the sensors. But yeah, great way forwards, absolutely.
Thank you both. I will bring this to Chris again. Chris?
Yeah, there's so many questions that are amazing coming in from the audience. And I think I would maybe just love to jump in on something that Peter brought up, which we've been talking about a lot as well in terms of the unknown unknowns. And so I think with these very exciting capabilities, we have the potential to do much more exploratory surveillance. And of course, we want to get these techniques and capabilities at the tip of the spear where they need to be. But what are your thoughts where, you know, we have these pathogens that are falling through the cracks in terms of existing tests and clinical triage and our ability to detect cases in humans? How can we adapt these towards the next novel virus, the virus that we don't really know is going to be zoonotic yet? What are your thoughts? Well,
let's look at an example. I mean, let's look at Nipah virus, for instance. We knew from surveys when we're working on Nipah virus in Malaysia and Hendra virus in Australia that there was something else going on because we're getting unusual cross-reactivity in the serum neutralization tests. So that gives you a clue that there's some other viruses out there. So you've got to do the in-depth viral discovery. You're always going to be held by what you know to some extent. But if you combine sort of PCR type approaches with deep sequencing of a number of samples, you should be able to get to the really true unknown unknowns. And whether those are significant to human health is a different issue. You know, and then one other example, SARS and COVID. We knew from SARS that there were related viruses and we could look at those in detail in the lab and see what they did. Expanding that out to all other coronaviruses from bats would give you a strategy to not only see what else is out there, but whether it's important or not. And there are simple things that could be done that are cheap and cost effective to really dig into those unknowns.
Thank you, Peter. Tim, do we have time for a few more questions?
You do indeed, for a couple more questions, I think.
Okay. Go ahead, Neon.
Wonderful. So there's one question here that is for both Joe and Peter. So the question is about the wearables. So is it feasible economically to deploy wearables, i.e. the wearable sensors for the whole human population to monitor the pathogen transmission?
I mean, these are all scalable technology. These are more political decision, and yeah. But technology is low cost and really very easy scalable. I mean, if you look at the example of diabetic, now they're deploying this at least 10 million of this CGM, continuous glucose monitor, company like Abbott or Dexcom, because there is the market need to monitor continuously fluctuation in glucose. So the technology is possible. You still need a good continuous reversible sensor for some of these protein, which is not easy to do it continuously on the skin. You can do it on a strip in the at-home testing, but monitor continuously protein is not as easy as a metabolite or electrolyte.
Well, look, I think a really important comment there on the political side, or really the social science side of this. Will people want to wear the monitors that we come up with? Will people want to have their health information beamed across and to some unknown person or known person with the idea it might leak out? In this current pandemic, we're seeing conspiracy theories around vaccines and chips placed in vaccines. People believe them. And, you know, if we're really interested in rural, remote areas, they're often places where people have less capacity to get access to information that would make them feel comfortable about these things. There's got to be some deep social science on what is acceptable to communities where we're concerned about the risk to the planet, but they're concerned about the risk to themselves. So I think we've got to deal with that sort of disparity front and center, and we've got to deal with the conspiracy theories front and center as scientists. We've got to push back on those two issues and really think them through. And that way we'll get better access.
Thank you, Peter. Thank you, Joe. Tim?
We have time for one more question. One more question, I think.
Chris?
Okay, I'll run with that. This one's near and dear, I think. It's a question from somebody listening in, and acknowledging that, of course, testing animal and potentially environmental reservoirs for pathogens is really important, but it seems like we really lack an understanding of the adaptive pressures on wild animal hosts in particular, and that we don't really recognize cross-species disease transmission that's even happening in the wild among animals, and other factors that sort of converge to create outbreak risk. What can we do? And I think this is also very relevant to NSF. What can potentially colleagues that are engaged in NSF work, what can they do to help us understand those factors better? Over to you, Peter.
Quickly, it's absolutely spot on. Our understanding, let's take bats, which are obviously involved in SARS and COVID, and a key risk in terms of they carry a lot of viruses and we interact with them in the wrong ways. We know so little about them. And, you know, years ago, you know, the idea of, is there a bat immunologist out there we can talk to? Of course not. And then you look at immunology of one species, does it extend to the other? And when you go into a bat cave, those caves are structured in a very detailed way, and that there are multiple species in there. There are nursery areas for the young. Different animals move at different regions every night. Those things need to be understood in a very deep way, and that goes across all the animals involved in livestock too, and disease emergence. So deep biology is needed, and understanding the social structures of those animals and how contact is made and how that will then lead to transmission is a huge area of work that people are involved in, but that needs to be brought in with all these other technologies and approaches, including the human behavior side, to really understand emergence. Really good point.
Maybe I'll mention briefly, the environmental part is a little easier. We have been doing a lot for the DoD to monitor a terrorist threat, to look for plumes and remote monitor prediction of the terrorist attack. Also in UCSD, we are analyzing the dormitory, the wastewater of the dorms to see if any localized events. So the environmental part is easier maybe than the animal that Peter mentioned.
Very well put. We can probably harness both, and I think attack on multiple fronts with the DoD analogy. That was a very exciting discussion. Thank you both. We really appreciate your time and your expertise and insight into this really important issue. Thank you.
Thank you very much indeed, Christine. Thank you, Joseph. Thank you, Peter. A round of applause from all 350 people around the world to you. Much appreciated.